Work and energy are a very involved and long unit. And in part one, I'm going to go over all of the basics. And then in part two, we're going to start to put it together. And if you understand the basics, by the time we get to part two, you'll see the puzzle pieces start to snap together and it should all start to make sense. So hang in there. As always, if you enjoy this content, give us a like and subscribe. So let's get right into it. When work is done, you get a change in energy. Now, the basics of work and energy, work is a scalar, so there's no direction, although we can have positive and negative work, and I'll get into that later. So therefore, energy also has to be a scalar. So all works and all energies are measured in the unit joule, and the abbreviation for that is a capital J. So if it comes after a number, it's a joule, and if it's just by itself, followed by an equal sign, then we're talking about impulse. But J after a number is the unit, the joule. So let's say that we did some work on an object, and the work that we did speeds up the object. So it makes it go faster. You get, in that case, you get KE. That is kinetic energy. So you can think of kinetic energy as energy of motion. Okay, what if we do work, and we do work to lift an object in a gravitational field? Well, if we do work to lift an object in a gravitational field, we get gravitational potential energy, PE with a little g. Now, sometimes the letter U, capital U, is used for potential energy, but for the most part, we're going to stick to PEG. So that would be gravitational potential energy. What if you do work to stretch or compress a spring? Well, in that case, you get spring potential energy, or PES, spring potential energy. And lastly, we have two situations where we can say work that occurs during a collision or work due to friction. These produce a type of energy called heat, and the symbol for that is Q. So this is a form of internal energy, and it is just heat. Now, the first three are called mechanical energies, and we'll define what that means later. And this is an internal energy because it's energy that is contained within the molecules of the object. So we're saying that work done to do these different things produces these different types of change in energy. But what's the formula for work? Well, work by itself is equal to F times D. Now, we can use H for height. We can use X for position. We could use X for spring stretch, but I'm going to use D for now as displacement. Work is a scalar, but displacement is a vector, as well as force. This is actually called a dot product, which means that we're multiplying the force that is parallel to the displacement. Now, there's one more piece to this, and we're going to be doing this for now only as a constant force or an average force. So we're not going to deal with forces that are changing unless they're changing at a constant rate. And I'll give you an example of that in just a second. So let's look at the unit. We have force, that's newtons, times displacement, that's meters. So that's what a joule is. A joule is a newton times a meter. Now, when we say the force is parallel to the displacement, what we mean is if we drag a block along at an angle so that F is here, our displacement, D, the force that's doing the work is the force that is parallel to the displacement. So in this case, that would be F adjacent side F cosine theta. And we'll get into more examples of that later. But for now, let's take a look at a graph. Let's say that we had a force that is changing at a constant rate. So here's our F, and let's say we go up to a certain displacement d. Well, because we know force times displacement is the work done, then the area has to be equal to the work. Now, if we did this for the average force, we could pick this in the middle and say that the average force times displacement would also be the work. Now, how quickly we do work is a completely different concept, and that's called power. So power is the rate at which work is done. So what does that mean, rate? Well, rate means something with respect to time. So if we're doing work at a certain rate, we're doing work with respect to time t. So the unit for this is the joule per second, and that has a name. It's called the watt, and the symbol for that is a capital W. But we can also do a mini derivation here and say that W is equal to Fd, and if we're doing this at a constant velocity, then we could say that the average force times the average velocity is also equal to the power. So let's say we had a graph of work and time. We know that P is equal to W over T, so that's our Y over X. So that means the slope, in this case, is equal to the power. So let's look at the formulas for these different types of energy. I'm going to stress this again, that work is equal to the change in energy, and we're going to look at all of this for a constant force or an average force. So if you want to know the kinetic energy at a moment in time, that's just equal to 1/2 mv squared. Now, the gravitational potential energy is equal to the mass times gravity times the height, but we choose what height 0 is. So our height 0 meters, that h is going to be based off of how far it is from 0. 1/2 kx squared, that x in this case is going to be from equilibrium. And when we deal with work by friction that gives us heat, that's going to be the force of friction times displacement. So when we deal with the change in energy, we need to look at the change of each of these values. So we'll start with kinetic energy. So we say that work gives us a change in kinetic energy. Well, we know that work is force, and we're going to deal with the average times displacement. But what speeds something up? What makes something go faster and faster? Well, that would be a net force. So we could replace this with ma equals delta ke. And we can do a little derivation here by stepping over to the side and saying vf squared equals v naught squared plus 2ad. And rearranging, solving for a, if we have an initial velocity of 0, that would give us a is equal to vf squared over 2d. Now, we can sub that in for a, so that we end up with m times vf squared over 2d times d. I left out the d here. That would be d, bringing that down. So what's that going to give us? Well, the d's are going to cancel out, and we're left with 1/2 mvf squared. In other words, the change in kinetic energy is going to be equal to 1/2 mvf squared minus what our initial was. Now, we chose it to be 0, so this was 0. So that's going to be v initial squared. So let's look at a very important subtlety here, which would be if we had a car, let's say a little cart, that is 2 kilograms, and it's moving along at 10 meters per second. And then it speeds up to 20 meters per second. And the question is, what is the work done? Well, we know that the change in kinetic energy is going to be our work that's done. So to do that, we're going to say 1/2 mvf final squared minus 1/2 mv initial squared, which is not 0 this time, is equal to 1/2 2 kilograms times vf squared, which is going to be our 20 squared, minus 1/2 2 kilograms times v initial squared, which is going to be our 10 meters per second. And if we do that work, that comes out to a change in kinetic energy of 300 joules. But the reason that I'm doing this problem is that I want you to see a subtlety that's very tricky, but at the same time very important. Let's say we have another cart, also 2 kilograms, but this cart speeds up from 100 meters per second to 110 meters per second. What would the work be in this case? Now, you might think, well, it went from 10 to 20, and that was 300. So a change in 10 meters per second should also give us 300. But you'll see that that's actually not the case. If we do this again, the change in kinetic energy is 1/2 mvf squared minus 1/2 mv initial squared. Then that's going to be equal to 1/2 2 kilograms times the final velocity, which is going to be 110 meters per second, minus 1/2 2 kilograms times 100 meters per second. And when we do the math on that, we end up getting a work which is equal to the change in kinetic energy of 2100 joules. Well, why did it take more work to speed something up 10 meters per second in the one case, but not as much work to speed it up 10 meters per second in the other case? And the reason is this. First of all, you can see it's because of this squared sign here, right? That's going to change things. But really what's happening is that to go from 10 meters per second to 20 meters per second, it's not going to travel as far. So the force that's making it go faster and faster, that's only going to be applied for a short displacement. Now, the car that's going 100 meters per second up to 110 meters per second, that's going to end up traveling much further while that force is applied. So that greater displacement means more work done. Let's look more closely at work done to lift an object. Now, we said that lifting an object a height is going to give it gravitational potential energy. And remember, when we're talking about height, we're only talking about the up. So if we were to lift this object over to here, our displacement is this distance, but the height is actually still the same. So our height, if we call our initial position 10 and our final position 30, then our change in height in this case is 20 meters. So what is Fd when we're dealing with gravitational potential energy? Well, our force that we're exerting is going to be an average force because we're going to lift it at a nice constant velocity. Well, if we're lifting it at a constant velocity, then what is the force that's lifting it? Well, we have the force of gravity down, and we have the force of lift up. So the force of lift up is going to equal the magnitude of the force of gravity down. So we can replace this g with mg, And we can replace this d with h. So that's going to be our change in potential energy. But when we talk about change in potential energy, we are dealing with the change in height. So really what we have is mg height final minus mgh initial. So the real definition of PEG is going to be mg, factoring out the mg, that gives us h final minus h initial, or change in height. So let's go ahead and put some numbers in and solve for this. So we say change in potential energy is mg delta h. So change in potential energy, that's going to be 1 kilogram times 9.8 meters per second squared times the height change, which is going to be 30 minus 10. So that's going to be our 20 meters. So our change in potential energy is going to be 196 joules. What is that? That's the work done. But what if we change up our situation here and we deal with a ramp? And let's say that this ramp is at 30 degrees and we have this 1 kilogram box, just like before, the same one, and the height of the ramp is 20 meters, just like before. So it goes up 20 meters. Well, if you do the math on this, you end up with a 40-meter ramp. So the question is, what's the work done? But I'm going to show you a different way to do it. What we could do is we could draw our force diagram and split this up as we've done in the past in the forces unit. And we know that that interior angle is 30 degrees. So the force to push it up at a constant velocity is going to be equal to this Fgx. And if we do our sine theta, so that's mg times sine theta, then our Fgx is equal to mg sine 30. So if you do the math on that and put in our 1 kilogram and our 9.8, then your Fgx comes out to 4.9 newtons. So if we were to find the work then what we could do is we could say W is equal to Fd, and the force that's parallel to the ramp, that's going to be 4.9 newtons, and we're sliding that up 40 meters. So what's the work done? Well, that comes out to 196 joules. That's not a coincidence, because the work is also equal to the change in potential energy. So that would be equal to mg delta h as we did before, and that also gives us the work, which is the change in potential energy, which is equal to 196 joules. This is only taking into account the situation without friction. So if we were to add friction, there would be additional work needed to be done to slide it up the ramp. For example, if there was friction, this force would be larger, producing more work, but the change in potential energy would be the same. So the difference would be the work converted into heat. And we'll do more of that when we get into conservation of energy. When we do problems where we do work on a spring, to stretch out a spring, it could also be to compress a spring, we get a new spring potential energy. So the work is the change in spring potential energy. So to do this, we have to be a little bit careful because we have to use Hooke's law. Now, Hooke's law is a direct relationship. So not all springs obey Hooke's law. Some springs, the force changes non-proportionally, but we're not going to get into that right now. So for right now, we're going to deal with springs where the force has a direct relationship. And let's go ahead and put in our FD. But when we put in our FD for this, that has to be the average force. That's going to be due to the force of the spring. and that's going to give us our delta PES. Well, what's the force of the spring? Well, the force of the spring is equal to Kx. But we've got a problem here because that's the force of the spring at a certain position. And we need to have the average force because as we stretch out a spring, the force changes, the force increases. So we need average force. So we can say that the average force of a spring is equal to Kx final minus Kx initial divided by 2. And we're going to do this for a spring that is stretched from equilibrium. So the initial position is 0. So we can say that the average spring force is equal to 1/2 Kx. So we can take this and sub this in for the force of the spring. So that becomes 1/2 Kx. That's the x from equilibrium. And the distance or displacement that we stretch a spring is defined as x. So our spring potential energy is 1/2 Kx squared. So we can rewrite that and say that our change in spring potential energy is equal to 1/2 Kx final minus 1/2 Kx initial squared. And if we do it from equilibrium, it's just this because that drops to 0. So let's go ahead and do a problem where we have a spring that's been stretched 0.2 meters from equilibrium, and then it's stretched an additional amount up to this new position. And we're going to say that K is equal to 2 newtons per meter. Now, we cannot simply do what we did before for gravitational potential energy. Whoops, that's a squared sign. We can't just simply say that the x is 0.4 because the distance change is squared. So that means that this value, we have to take into account this changing force. So how do we do this problem? Well, all we do is what we've done before, which we say the work turns into this change in energy, which in this case is PES. So we have 1/2 Kx final squared minus 1/2 Kx initial squared, and that's our change in spring potential energy. So that's going to be 1/2 2 newtons per meter times 0.6 meters squared minus 1/2 2 newtons per meter times 0.2 meters squared, and that's our change in spring potential energy. That comes out to a value of 0.32 joules. Now, here's another type of problem that's given, and sometimes this is done actually as a lab, which is to ask you to find the spring potential energy gained when we hang a mass on a spring. So we're not given K in this case, and we just have a spring that's hanging there, and then we put a weight on it, and the weight ends up stretching the spring down so that the spring ends up gaining spring potential energy. So let's say that this change in length is 0.5 meters, and we're going to call that our equilibrium. Well, we can't do PES equals 1/2 Kx squared because we don't have K. So what we're going to do is Fs is equal to Kx, and we know that the force of the spring when it's down at the bottom is at rest, so the force of gravity is equal to the force of the spring. So we can say that the force of the spring is equal to mg, or 2 kilograms times 9.8 meters per second squared. And that's going to be equal to K times the amount it was stretched, 0.5 meters. So that gives us a K of 39.2 newtons per meter. So now we can find our change in spring potential energy, which is equal to 1/2 Kx final squared minus 1/2 kx initial squared, and since it starts from an equilibrium of 0, that's just 0. So our change in spring potential energy is equal to 1/2 k that we just found, 39.2 newtons per meter, times 0.5 meters squared. And that change in spring potential energy is equal to 4.9 joules. I don't want to finish with springs just yet because springs can be extremely tricky, and I'm going to show you where physics exams like to trick you up. And here's the problem with this particular situation. We have a spring that starts at equilibrium and then it's stretched to 0.5 meters. And we have a spring constant of 20 newtons per meter and it's stretched 0.5 meters. So that means that the force of the spring is 10 newtons. So if we do this, W is equal to F parallel D, and we put in our 10 newtons and multiply that by 0.5 meters, we end up with a work done of 5 joules. But this is wrong. This is not the right answer. And the reason is because we didn't use the average force. So let's go ahead and do that with the change in spring potential energy method. And that's going to be 1/2 kx final squared minus 1/2 kx initial squared. It starts at 0. So our change in spring potential energy is 1/2 20 newtons per meter times our x final, 0.5 meters squared, and we get a different answer. We get 2.5 joules. Well, why? Because the force of the spring of 10 newtons is only the force right here. The force at the beginning was 0. So as the spring was stretched, the force increased. What did the force do? The force increased from 0 up to 10 newtons. So it did that. And at 10 newtons, that's where our 0.5 meters is. So that's our F, and that's our X. So what do we have to do? If we want to use this formula, we have to use the average force. Well, what's the average from 0 to 10? The average from 0 to 10 is 5. So when we say FD, we have to use 5 newtons times 0.5 meters. So the work comes out to 2.5 joules. So this was wrong. This ends up agreeing with our change in potential energy. We also could have graphed it and found the area under the curve. In this case, that would be the work. When we deal with collisions, the only way to solve these problems is to look at the energy that we started with and compare it to the energy that we end with. So in this case, we have two balls that are traveling along towards each other, and we know that they're moving, therefore they have kinetic energy. So the sum of the energy of the system is going to be the sum of the kinetic energy. Now, the momentum would be positive here and negative here, but remember that energy is a scalar. So the energy to the right is going to be added to positive energy to the left. These are both positive energies. Now, the balls crash into each other and stop. So all of that energy gets converted into heat during the collision. So to do this, to find Q, to find the heat, what we need to do is find the total kinetic energy. Well, the total kinetic energy is going to be equal to 1/2 mv squared plus 1/2 mv squared. That's going to be the kinetic energy of the two balls. So that's going to be 1/2 of 2 kilograms times 2 meters per second squared plus 1/2 2 kilograms times 2 meters per second squared. And when we sum that all up, that total kinetic energy is 8 joules. Well, we know that the kinetic energy in this case, the total kinetic energy, gets converted into Q. So what then is Q? Q is 8 joules, and we can also call that the internal energy of the system. That would be the molecules would now have that energy inside the balls. The other way that we can produce heat is with kinetic friction. So if we have a block, and let's say that the block is moving along, it's a 2 kilogram block, and it's moving along at 2 meters per second. Let's say it slides to rest over a distance of 10 meters. Well, which direction would the force of friction be acting? Well, if it's slowing down and it's moving this way, then we know that the force of friction must be acting to the left. So the force of friction in this case would be 0.4 newtons. I just made that up, 0.4 newtons, so that we can figure out the work done. So we're going to say that it slides to a stop. And so we know that the change in kinetic energy is going to be equal to the heat produced. And we know that change in kinetic energy is final minus initial. So if we start with this, our final is 0 and our initial is what we started with. So our final drops out to 0. So we have a minus 1/2 2 kilograms times 2 meters per second squared is equal to our Q, or our change in kinetic energy is equal to minus 4 joules. So we lost 4 joules of kinetic energy, but we gained 4 joules of heat. Now, we could have done this another way. We could have also said that work is equal to the force of friction times the displacement. So we could have said that the change in kinetic energy is going to be equal to the negative 0.4 Newton force, the force to the left, times 10 meters. And that would give us a change in kinetic energy of minus 4 joules. Or again, our Q would end up being a positive 4 joules. So when we have a force, when F is opposite the displacement, the energy ends up being negative, telling us that we lost that energy. Coming back to two major distinctions between types of energy are mechanical and internal. So mechanical energy can be transformed into another type. For example, if we have a block or a ball that's up in the air with height, it has energy, and when we let it go, it can turn into kinetic energy. So it can be transformed into one form into another. And there's three main types in physics: gravitational potential, kinetic, and spring potential. Whereas with internal energy, this is energy that cannot be recovered. So once an object gains heat, that heat can't turn back into kinetic energy, for example. It can't turn back into spring potential. So that gets us to the idea of conservative and non-conservative forces. So a conservative force is defined as a force that conserves mechanical energy. In other words, there's no heat loss. And the two main types of conservative forces are the force of gravity and the spring force. These forces are the forces that can get us our energy back. Non-conservative forces, on the other hand, cannot. So mechanical energy is not conserved because the energy becomes heat. And examples of those are the force of kinetic friction and also drag forces like air resistance. So let's look at a couple of examples of this. So if we have a force that stretches out a spring, the spring gains spring potential energy. But during this process in which the force was dragged out to the right, this did positive work, but the force of the spring did negative work because the force of the spring was opposite the direction of the displacement. So when we have a negative force of spring opposite the displacement, the work done by the spring is negative. However, because it is a conservative force, that force can then produce a new form of energy. We can take that spring potential energy and convert it back into kinetic. Think about the spring being released, then the mass would accelerate in the direction of the spring force and turn into motion, in other words, kinetic energy. We can look at another example of lifting a weight. For example, if we have a mass that we lift at a constant velocity, the lift force is in the direction of the displacement. Therefore, that work is positive. But the force of gravity is opposite the displacement, so therefore that work being done is negative. Gravity does negative work. But if we then take that object and we release it, that object will fall and gain speed. The force of gravity is now in the direction of displacement. As a conservative force, it's transforming the gravitational potential energy into kinetic energy as it goes faster and faster. So the work done by gravity in that case is positive because the released potential energy is converted into kinetic. One final energy to stress the idea that the work done is done by the force that's parallel to the displacement. Let's say we have a constant force of 20 newtons, but it's acting at 60 degrees on a block. Well, it's not the 20 newtons that's doing the work because the displacement is not parallel to this 20 newtons. So we need the force that's parallel to the 5 meters. So we need to make a right triangle and figure out FPX. So what's FPX? We use cosine 60. That gives us a force in the x direction of 10 newtons. So now all we have to do is force parallel times displacement, and we can say 10 newtons times 5 meters. So our work done in that case would be 50 joules.